Okay, so this is section 15.6. This will be video number 2. This one should go much quicker than the first one, and it will be quicker than the last one. We're going to do 3 examples. The first 2 will be very simple, and the reason for that is because we're trying to find the area of the surface of z equals 2 plus 3x plus 4y. That's just a plane. So finding the surface of a plane really is not going to be that challenging to do. And they're going to give us the domain as 0 to 5 and 1 to 4. So it makes it very simple to do. Typically, if they're giving you the dimensions in this case, they usually do them in order. So this would be your x, this would be your y. Otherwise, it's going to be explicitly said as x and y. So we don't even really need to sketch this. You certainly could go ahead and sketch it if you want to, but this one's pretty straightforward. We're just going to use the formula which says that the surface area is the double integral over our domain of the square root of 1 plus, let's see, the derivative or partial derivative with respect to x. Well, the partial derivative of this thing here with respect to x is just 3 squared, plus the partial derivative with respect to y, which is just 4, and then we square it, and then dy dx or dx dy. It doesn't really make any difference in this case. I think I'm just going to go dy over dx. I mean, sorry, not over dy dx. It doesn't really matter. So then the y bounds are 1 to 4, and the x bounds are 0 to 5. And what makes this so easy is that when you're taking partials with respect to a plane, you're going to end up with constants underneath. Makes it really simple. So let's see, that's going to be, what is that? 1 plus 9 is 10, plus 16 is the square root of 26. That's a constant. It can be pulled all the way out to the front. And then really what I have left in there is just a 1 dy dx. Okay, we can actually, because these are constant bounds and the variables are separable, we can split it up. So we're going to have the square root of 26 integral from 0 to 5 of dx times the integral from 1 to 4 dy. So then that's going to be the square root of 26. Integral of dx from 0 to 5 is just going to give you 5. Integral from 1 to 4 of dy is just going to give you 4 minus 1, which is 3. So 3 times 5 is 15 times the square root of 26. That would be the surface area of that plane over the domain 0, 5, 1, 4. Okay, really very simple. Number 2 won't be much more difficult. We do have a little bit of extra stuff that we have to deal with here. This one we're probably going to want to sketch. So it says find the area of the surface of the plane 3x plus 2y plus z equals 6 that lies in the first octant. So instead of giving us bounds, they actually just told us this thing was in the first octant. So what makes that difficult is we have to figure out the bounds based upon the plane. So this is one we're going to want to sketch the plane. It's only in the first octant, so that's the only part I have to worry about. So let's find the intercepts. The x-intercept is when y and z are 0, so that's really 3x equals 6, so x is going to equal 2. So the x-intercept is out here at 2. The y-intercept is when x and z are 0, so that means 2y equals 6 or y equals 3. So there's my y-intercept. And then the z-intercept is when x and y are 0, so z is going to equal 6. So 1, 2, 3, 4, 5, 6 are right up there. So we are talking about the surface area of this plane right here. Okay, and why is that important? Let's mark these. That's 3, that's 2, that's 6, because this is going to allow us to figure out our bounds now. If we look at the projection of this plane down into the xy plane in 2 dimensions, it looks like we've got a 3 up here and a 2 down here. So the projection looks something like that. So the question is, do I want to do this as a type 1 or a type 2? I think I'm still going to go with a type 1. You could pick whichever one, it doesn't matter. Go with a type 1, which means that y is going to go from one function to another function, and x is going to go from a value to a value. So the question is, what is that function? Well, let's see, it's going to be y equals, the slope is going to be down 3, right 2, so it's going to be a negative 3/2 x, and then the y-intercept is 3. So that is the upper bound. The lower bound is quite obviously 0 because it's the x-axis. So it looks like we've got everything that we need now to create our surface area. It's a double integral. So x is going to go from 0 to 2, right? Because that's 0, that's 2. Y is going to go from 0, yeah, or the x-axis, up to negative 3/2 x plus 3. And that's going to be of the square root of 1 plus, let's see, the partial with respect to x is 3. The partial with respect to y is 2. And then I said I was doing type 1, so it's dy dx. Okay, not a big deal. Now, only thing we can't do here is separate the bounds, separate these things because of the fact that the bounds are not all constant. But I can still pull the square root part out front because that will be constant. So that's going to be 1 plus 9 is 10 plus 4. So square root of 14 out in the front, 0 to 2, 0 to negative 3/2 x plus 3 of 1 dy dx. So antiderivative first with respect to y is just going to be y from 0 to negative 3/2 x plus 3 dx, 0 to 2, square root of 14, don't forget all that stuff. So plugging in the upper bound is going to give us negative 3/2 x plus 3. Plugging in 0 leaves you with nothing. So then we have to do the antiderivative of that with respect to x. So let's see, that'll become negative 3/4 x squared plus 3x evaluated from 0 to 2. Don't forget the square root of 14. Plugging in the 0 is going to end up giving us nothing, so we just have to plug in the 2. So we get the square root of 14 times, let's see, 2 squared times negative 3/4 is just going to be negative 3, plus 2 times 3, which is 6. So it looks like we're just going to get 3 root 14. Now, if we didn't want to do the antiderivative, you probably could have noticed that integrating this right here was literally just finding the area of that triangle. Because I'm integrating from 0 to 2 underneath of this curve right here. That's just the area of that triangle. Okay, you could have done it that way as well, and that probably would have made it even easier because the area of that triangle, since that's a 3, is 2 times 3, which is 6, divided by 2, which is 3. So it would have been an area of 3 multiplied by the root 14 from the beginning one. Either way, would have been fine. Okay, one more. Find the area of the surface of the hyperbolic paraboloid z equals y squared minus x squared that lies between the cylinders x squared plus y squared equals 1 and x squared plus y squared equals 4. I'm going to do my best to sketch this. So let's see, we've got 2 cylinders. Both of them are revolving around the z-axis. So you're going to have a cylinder, which I guess would be your outer cylinder. That's the x squared plus y squared equals 4. And obviously it goes on forever, but just for purposes of here, I'm going to stop it there. Then you've got the inner cylinder, which is going to be in here. And it kind of makes this like basically hollowed out tube, I guess you would say, something like that. And then what you've got, and I guess I'll finish this off back there so you can see that this is all the way around. Then what you've got is this hyperbolic paraboloid, which must intersect this cylinder somewhere. Now, again, it's a hyperbolic paraboloid. Kind of looks like a Pringle. Not going to be easy for me to draw, but the thing you want to recognize is that it's going to be curved as it comes down towards this cylinder. in some fashion, and maybe it's curving up as it comes from this direction. But whatever this thing looks like when it hits the cylinder, it's going to create some kind of a circular region, but that circular region in here is probably not going to be flat like the way I have it. As a matter of fact, it won't be. And what I'm going to show you real quick is something on CalcPlot 3D, which gives a much better representation of that. So here it is on CalcPlot 3D. Here's the outer cylinder, here's the inner cylinder, and here is your Pringle chip or your hyperbolic paraboloid. So if you kind of turn this and look straight down into it, you can see that it's curving. It's curving down in this direction in between these two cylinders, and it's curving up in your, I guess you would say, in the X direction in between the two cylinders. So we're looking for this surface area which lies in between the two cylinders and doesn't actually even touch the outside cylinder and part of it. There's actually a gap here, but this is what we're looking for, is the surface area out here, but not past this outer cylinder. So hopefully that gives you at least somewhat of a good visual representation of what this thing is, because that was a really hard one to draw, as a matter of fact. Although I don't think I did too poorly, just my cylinder didn't curve in here. But there you go. All right, so how are we going to do this one? Well, we are going to have to figure out bounds. Considering that these things are bounded by cylinders and they're circular, I'm thinking that our domain here is probably best described in polar. So our domain, because it's going to be something which looks similar to that, I mean, that's the region we're trying to find the surface area of, something like that, I'm thinking polar. And I think that will make this one quite a bit easier. Okay, we're still going to go ahead and take the partials with respect to x, but then we'll change them into polar coordinates. So let's see, what would our bounds be? Well, let's see, we're going to have a radius of 1 here and a radius of 2 out to there. So the radius of this thing goes from 1 to 2. And theta, because we're talking about r's and thetas, theta, it's a complete circle. It's going to go all the way around. And remember, if you project this thing down into the xy plane, it will look circular, even though it's curved on the inside. So theta is going to go from 0 to 2 pi, because we're going to go all the way around the circle. So we've got our bounds. R goes from 1 to 2, theta goes from 0 to 2 pi, of the square root of 1 plus, let's see, the partial of our surface, this is our surface, with respect to x is going to be negative 2x squared. The partial with respect to y is going to be 2y squared. And now we're doing this with respect to polar. Now polar, remember, is r dr d theta. Okay, you have to have that extra r in there. So let's go ahead and change this stuff in here to polar. Well, if I were to square the inside of that stuff, I would get 1 plus 4x squared plus 4y squared. But x squared plus y squared, 4 times x squared plus y squared is another way I could write that. X squared plus y squared in polar is r squared. So really what I have on the inside of here is the square root of 1 plus 4 r squared, r dr d theta. All right, so now we're ready to do this. It looks like we're going to have to use u substitution. So u is going to be the interior 1 plus 4r squared. Du would be 8r dr. So dr is going to be du over 8r. Okay, so now we're going to have the integral from 0 to 2 pi. We can change the bounds if we want to. Probably be the easiest thing to do, I would think. So our new u bound here is going to be, let's see, if I plug a 1 in for r, that's going to give me a 5. If I plug 2 in for r, that's going to be 2 squared, which is 4, times 4 is 16, so 17. Square root of u times r, dr is du over 8r, and don't forget I've still got the d theta. So the r's are going to cancel out. I can pull the 1/8 all the way out to the front. And then I'm going to have to take the antiderivative of the square root of u, which is u to the 1/2. So it's going to be u to the 3/2 times 2/3. We'll evaluate that from 5 to 17 d theta. I guess I probably could have separated this stuff, but it won't matter. I'll pull the 2/3 out to the front, and that's going to give me, was that 2/24 or 1/12? Integral from 0 to 2 pi of, let's see here, that's going to be 17 to the 3/2 power minus 5 to the 3/2 power d theta. That's just a constant, so the antiderivative is just going to give us 1/12 of that. Times theta, evaluated from 0 to 2 pi. Plugging a 0 in would wipe that out, so just plugging in the 2 pi, it looks like I'm going to get 2 pi times the 1/12, which would actually give me pi over 6. So pi over 6 times 17 to the 3/2 minus 5 to the 3/2. That is not a very pretty answer, but that is the answer. So that's the surface area of the area in between the two cylinders of the hyperbolic paraboloid. Oops. All right, that video is actually a little bit longer than I anticipated it. The last video will be the shortest, then it's going to be about 15 minutes or so to do the surface area of a sphere.